Okay, so let's resume this morning session. This is the last talk of the optics, the session dedicated to optics. And our speaker is Auro Perego from Aston University, where he currently holds a 5-year fellowship from the Royal Academy of Engineering. And he will talk about wave amplifications by asymmetries in nonlinear photonic systems. Stage is yours.
Thank you very much for the kind introduction, and thank you for inviting me here at this beautiful workshop. So my name is Auro Perego. I work at Aston University, and I will be talking about some methods to amplify waves, introducing asymmetries with particular focus on photonic systems. So this is the outline of my talk. I will give a brief introduction about well-known phenomenon of modulation instability in the nonlinear Schrödinger equation. And then I will describe how frequency unbalanced losses for signal and either waves can produce instability and can be used for generating interesting states of light for applications in the context of photonics. And then I will discuss some of the relations of this phenomena to the converse symmetry breaking phenomenon for coupled oscillators. So an optical fiber is basically a glass pipe where you have a core inside and surrounded by cladding, and the refractive index of the core is larger than the one of the cladding, which enables guiding light along the core through the phenomenon of total internal reflection. And if you have a fiber with a spatial coordinate z, then the evolution of the electric field, the slowly varying envelope A along z, is described by the nonlinear Schrödinger equation. And here we have two main effects. Beta 2 is the so-called group velocity dispersion coefficient, describing the physical fact that different waves travel at different velocity along the fiber. T is a temporal coordinate in a reference frame co-moving with the light pulse. And we have nonlinearity with the coefficient gamma. This is due to the fact that when light propagates inside the fiber, it modifies the refractive index, and this modification acts back on the propagation properties of the light itself. So modulation instability is a well-known topic, and I think I'm not the best person to introduce it to such an audience where there are many experienced people. But anyway, I think to the best of my knowledge, it was first noticed by Bogolyubov in a 1947 paper when he was studying the spectrum of excitations in a Bose-Einstein condensates, and he noted that for a particular sign in the dispersion relation, you may have instability. But he didn't go further about this in his paper. And then Benjamin and Fair described it in fluid dynamics, and Zakharov and his school in hydrodynamics and plasmas, and in photonics there was work by Bespalov and Talanov. And it is an ubiquitous phenomenon in physics due to the universality of the NLSC and its generalized form. And it occurs in the focusing regime, where you have anomalous dispersion, so negative sign of beta 2 in fiber optics notation. And in this case, a powerful input wave, the condensate or the pump, as you call it, will become unstable with respect to symmetrically detuned frequency sidebands, resulting in wave destruction and sidebands amplification. And this is related to many important phenomena, such as Fermi-Pascal single recurrences, solid tones, turbulence, rogue waves, and so on. So what people do in general, they take the homogeneous solution, time-independent solution to this nonlinear Schrödinger equation, add some small perturbations oscillating at frequency omega, insert this ansatz into the equation, linearize with respect to perturbations, and get an expression for the gain. And the gain has two symmetrical lobes with respect to the input wave frequency. And here you have an example of spectral evolution where you have generation of the two sidebands and then some huge spectral broadening. And in time domain, you have a modulation pattern with the periodicity given by the inverse of this maximally unstable frequency. So this is not just a topic that is of interest for mathematicians or physicists. People try to develop technologies based on this. So they want to amplify broadband signals for optical communications, and they take a Benjamin Fair unstable fiber, so to say, they inject a powerful pump wave and many other waves with low power that are signals carrying the information for your internet, for instance. And then exploiting this gain dynamics, they can amplify the signals at the output. And they can also generate spurious waves here on this side of the spectrum that we call the idlers. And there is ongoing research. We have this at Aston. There are many groups in the world doing this with the purpose of developing devices. And I want to ask the question, what about losses? So are they a stabilizing factor? One would think that yes, if I put losses at a certain frequency, I will reduce the gain of the Benjamin Fair spectrum. And this is the case for focusing an LSC, both for symmetric and asymmetric losses for signal and idler waves. But things are more interesting in the focusing case, where symmetric losses just cause negative gain, which means that the noise at the lossy frequencies is reduced. This is quite boring and trivial. But if you put asymmetric losses, then you may have positive instability increment on both sides of the spectrum. And this is what this talk is about. So one can think of designing a device where you have a particular photonic system or waveguide or whatever that has a strong absorption located at certain frequency, omega A, and you pump it with a different frequency, omega P. And then at the output, you collect a spectrum which exhibits two additional sidebands, one located in the vicinity of the losses and one symmetrically located. So this is the general concept, and one can formalize it mathematically by considering an optical fiber, which is doped homogeneously with the set of atoms or resonant two-level systems. And from Maxwell-Bloch equations, you can end up under certain approximations with a nonlinear Schrödinger equation containing a convolution term which describes a filter that acts in frequency domain. And then if you calculate the linear stability, the solution, the homogeneous solution, and then the linear stability analysis, you get the gain spectrum. And here it's plotted as a function of frequency and the function of filter position with respect to the zero mode. And this gain follows the filter, basically. And here are some examples of simulated spectra corresponding to various filters shown here in the insets. And if you propagate the thing for long enough, then you get also additional sideband generation. So this is just a kind of proof of concept idea, and one could think of different, more feasible geometries, having, for instance, a piece of fiber without filtering, then put a lumped filter, another piece of fiber, and so on and so forth. And then you can try to map the filter loss profile into a gain profile in the spectrum. And this is not limited to kernel linearity. It could work also for quadratic nonlinearity. So these are equations for an OPO, optical parametric oscillator. You have two waves, signal and idler, and delta K is the mismatch parameter, which rules the interaction between the waves and the pump. Then you have coupling coefficients and the losses, and you can calculate the gain. And when you have zero losses on the idler and zero losses on the signal, you have gain only in the vicinity of delta K equals 0. This is the so-called phase match operational regime, which is how these devices operate in general. But then if you increase asymmetry of the losses by putting losses on the signal, then you reduce the phase match gain, but you amplify waves for different frequencies as well. So you have this asymmetry, dissipative asymmetry leads to broadening of the gain spectrum. And for every mismatch parameter, you can find the value of the asymmetry that maximizes your gain. So there has been a series of works, not many though, in optics and photonics about this phenomena. Here is a list of what I believe are the most representative ones. And people tried also to use this idea to amplify matter waves in Bose-Einstein condensates by momentum resolved dissipation in this paper here. And I want to talk more in detail about how to use this concept to generate optical frequency combs, which are an important or interesting state of light for many applications. So optical frequency combs, Dimitri talked about it before. They are a Nobel Prize winning technology, which consists in the set of coherent, equally spaced frequency laser lines. And they find many applications in metrology, spectroscopy, optical clocks, molecular fingerprinting, optical communications, and even exoplanet search. And they can be generated by mod-locked pulsed lasers or by passive-driven optical resonators, and in nonlinear fiber optics too. And the idea is to consider an optical resonator where it's basically a closed loop where light circulates inside multiple, surviving for multiple round trips, as Dimitri has discussed before. And you have some coupler here where you inject a wave and light circulates here. And we consider a resonator which is as a dispersion that makes it Benjamin Fair stable, so you don't have in general instability or you don't have Turing instability. And you inject a single frequency, pump wave that resonates here. And if the resonator has a spectral filter that causes narrowband losses at a different frequency, then this loss asymmetry can generate two spectral sidebands, one in the vicinity of the filter, one symmetrically located with respect to the pump. And then through cascaded four-wave mixing, you can populate a vast set of cavity resonances. So you have a comb, and all these lines are coherent. And most importantly, if you are able to, in your device, to control the frequency detuning between your pump wave and your filter position, then you are able to tune the line spacing of this comb. And this is important for certain applications. And also what is important is that this approach works in the normal dispersion regime. So you don't need, from practical point of view, to do some complicated dispersion engineering that is needed in microresonators when the material dispersion dominates, which is normal. So it could have potential for the visible part of the spectrum too. So an experiment has been developed in collaboration with the group of Lille, of Arnaud Mousseau, to test this idea in practice. And fiber loop was built, fiber resonator, 100-meter long roughly, and with the normal dispersion regime, so you don't have the standard Benjamin Fair instability. And we used an intracavity spectral filter to cause losses at a frequency detuned by about 400 gigahertz from the injected pump wave. And here is an example of the filter transmission profile. And most importantly, here we have a frequency-dependent phase profile that is associated by the frequency-dependent losses via the Kramer-Stronig relations. And one can make a theory, a model for this system based on the so-called IKEDA map. So you solve the nonlinear Schrodinger equation for one round trip, then you apply boundary conditions, including the injected pump frequency, coupler losses, and phase shift that accounts for the phase accumulated by the field upon propagation modulo 2 pi. And we have a convolution term which describes the interaction with the spectral filter. So with this formalism, you can calculate stationary solutions, and you can perform a stability analysis and calculate the instability gain. And exactly, and this is an exact formula that is quite long, so I don't report it here. But you can also notice that the filter phase here plays the dominant contribution to the gain. So you can basically come to a single compact equation for which describes which frequencies are amplified. You can neglect in the first approximation the losses in the filter and take only the phase to come to this phase matching relation where you have a filter phase term that compensates for nonlinearity and dispersion. So basically we have that asymmetric losses for signal and either waves induce a frequency dependent phase, and this enables directly waves amplification. And you can see some examples here. This first plot is from experiment. The red line is an optical spectrum consisting of a series of lines, and the dotted line is the filter transmission function, and this is some simulation results as well. And you can see that the gain is in the vicinity of the filter. And in time domain, you have a train of pulses on top of a CW background, and with a periodicity which is the inverse of the comb line spacing. Most importantly, you can test the tunability hypothesis. And in this case, we were playing with a tunable laser by changing its wavelength such that the frequency difference between the laser and the filter was changed in different execution of the experiments. And you can see here a zoom on the primary comb sidebands. And you can see that every color corresponds to a different pump wavelength used. And you have always a frequency generated in the vicinity of the filter. And then as you move the pump away or closer, the idler generated moves as well. And we achieved more than 100 gigahertz tunability that is plotted here versus the detuning between the pump and the filter. Here, the dots are experimental points, and the continuous line is the theory that I described before. And also, if you love to get more simple models, you can average out the boundary conditions and come to a single mean field equation, which is called the generalized Lujato-Lefebvre equation, which accounts for all the physical effects, including loss, detuning, filter loss, filter phase, dispersion, nonlinearity, and injection, all in a single model. This gives you a more compact analytical formalism. It's basically a generalized form of a damped-driven NLFC. And you can see that this mean field model reproduces well the results of the IKEDA map in terms of spatiotemporal pattern formation. And also, if you plot the parametric gain as a function of frequency and different parameters in the system, you get a very, very good agreement. So this is also nice. And finally, I want to say a few words about the relation of these ideas to the concept of converse symmetry breaking. So this is something that has come out from this paper by Nishikawa and Motter in 2016. And in their own words, is the scenario in which complete synchronization is not stable for identically coupled identical oscillators, but becomes stable when and only when the oscillator's parameters are judiciously tuned to non-identical values, that by breaking the system symmetry to preserve the state symmetry. So basically, they observe, studying set of coupled oscillators analytically and numerically, they observe that they had synchronization only but when a certain degree of diversity or heterogeneity was introduced, while for the same set of parameters, they could not observe synchronization. So they demonstrated this experimentally with electromechanical oscillators. They showed that this idea enhances stability in synchronization in various systems, and including in power grids, which I found very, very interesting. Anyway, the idea is to connect with these works that I was mentioning before in photonics, and you can consider an example where you have kernel linearity with two equations for the signal and idler that can be recasted in the coupled oscillator form, and assuming, like in the case of optical frequency comps, that losses induce the phase shift, and the phase shift is the dominant asymmetry to calculate the gain, then these coupled oscillators equations are symmetric or invariant under transformation AS going into AI and vice versa with the complex conjugation. And if the diversity parameters are equal, diversity parameters describe the impact of asymmetry, then related to the filter, then you don't have amplification. But then if you introduce asymmetry, you can have locking and amplification. Basically, here there is a plot of the instability gain, which corresponds to synchronization between the sidebands as a function of frequency and as a function of these diversity parameters between the two oscillators. And in the colorful area, you get gain and locking, and in the dark area, you get no gain and no locking. So here's an example of the sidebands dynamics as a function of the evolution coordinate. For the unlocked case, there is no growth, and the relative phase between the sidebands varies, changes over propagation. While when the two, when you introduce asymmetry, you get amplification and phase locking. And similarly, for the quadratic nonlinearity case, you have again the similar asymmetry, and you can have a locking map where the presence of asymmetry broadens the value of delta K area for which you have locking and amplification. And again, you can see here some examples where in the unlocked case, the phases drift, the relative phase drifts, and there is no growth, while when asymmetry is introduced via losses, then you can get locking and amplification. So basically, this asymmetry and diversity can lead to symmetric phase locked states. And in the set of heterogeneous set of couple oscillators, you have stable and synchronized states. And in the case of coupled optical waves in medium with asymmetric spectral response, you can get amplification mediated by the locking enabled by the asymmetry. So, and coming towards conclusions, all what I talked about could have various possible directions. Definitely in the field of photonics, there is interest for miniaturization for applications of frequency comb generation. Multi-mode amplification, so far I consider only 2 modes. You can consider a highly multi-mode system as well with asymmetries, and study of multi-mode converse symmetry breaking in disordered photonic systems too. There is the problem of turbulence, if to be studied, if it differs and how it differs from the standard one. And there is big opportunity to look for systems beyond photonics, and possibly, and my suspect is that similar phenomenon, given the simplicity of the models, would have been already observed in other fields, in hydrodynamics or in other related fields of nonlinear science. So I would be happy to discuss this with the experts from various areas. And so to conclude, basically, asymmetries enable wave amplification in nonlinear dispersive systems described by universal formalism. We can engineer dissipation and gain from losses, developing novel photonic technologies. So, and asymmetry may enable a synchronization in contexts where this would not be possible without it. And here are some references about our works that we did in this area. And this was not a kind of lone work. I worked with Sergei Turitsin at Aston, with Kestutis Staliounas and UPC in Barcelona, and especially with the group of Lille of Matteo and of Arnaud Mousseau and Matteo Conforti on the experimental implementation. And I would like also to thank you again for the invitation, for your attention, for your patience. Thank you.
Any questions?
The filter function that you have shown on one of the first slides was much narrower than the spectrum that was generated.
Yeah.
Is it fair reflection of what was in the experiment?
Yes, because the filter induces a local modification of the dispersion relation, and there is an optimal frequency around its position that is amplified. Mm-hmm. So basically, you can see the filter as a frequency-dependent modification of the dispersion relation, and different frequencies experience gain, but there is one frequency that experiences most gain. So this will win the competition.
Is it controllable, the bandwidth of the filter? Can you expand it by several? I don't know.
In numerics, yes. In experiment,
no,
I don't know. In experiment, I think there are. So if you make an experiment in micro resonators, I think it's difficult. But in fiber resonators, you can insert in the cavity a programmable filter, and we are thinking of doing it, where you can control the frequency position of the maximum losses, and also the width, and also the chirp. So you can really, potentially, you can tailor a lot. Yes, and this will alter the phase matching condition. So if I plot the parametric gain calculated from the mean field model or from the Ikeda map, I can plot it versus the filter width, and I see big changes. So it changes the position of the gain, it changes the strength of the gain as well.
I see. Okay.
Any more questions? A curiosity about these oscillators, this model of oscillators. So what is the coupling they consider, like the field coupling?
In the historical paper,
yeah.
I think it's just the standard coupled pendula with the sinus. They also consider coupled Stewart-Landau models in their supplementary. I think, yes.
Right.
I will share the reference. Yeah.
Okay, so this is the model you would like to.
Yeah, in my case, I just consider the two sidebands which can be mapped into simple oscillators, and in my case, the coupling between the sidebands is given by the nonlinearity. For instance, when they did the work on the power grids, that they have a particular equation that is called the swing equation, which is similar to couple oscillators equation as well. I think it's a quite universal thing. I would expect this to happen in a variety of coupling scenarios.
Any more questions? If not, let's thank Auro again.
Thank you.
Now we move on to the next session, which is on cover oceanography and regarding session.